Hello everyone, it's Richardson here in Sun Science again. So in my previous video I discussed about the electrocyclic reactions. So I have made the video so you can watch that. And today in this video we are going to particularly concentrate upon the cycloaddition reactions. Okay, it is the another type of cycloaddition reaction. Okay. So in the later on coming videos I'll be covering all the types of reactions in the pericyclic reactions. Okay, so stay tuned. And today let's go into the topic, that is the cycloaddition reactions. Yeah, from the name itself you can identify what does it mean. Okay, so it is a cyclic addition reaction, right? It is also comes under the category of a pericyclic reaction where the combination of two unsaturated species in presence of light and heat is involved. So you call that reaction as a cycloaddition reaction. So here you have two unsaturated species, right? And it is induced by thermal or photochemical. So you will call it as a pericyclic reaction. Okay. Now, so you can notice that the reaction involves the addition of a system of m pi electrons to a system of n pi electrons. So I told you it has two unsaturated species involved. Let one be with m pi electrons and the other species be with n pi electrons. So this is your reactant 1 and this is your reactant 2. Okay, your two unsaturated species. So the resultant product is a cyclic product with this many pi electrons, that is m plus n minus 4 pi electrons. Okay, so let me say for example, so I have a alkene over here, unsaturated species. You have ethylene molecule here. So it is a 2 pi system and this is a 2 pi system. So we know how we are calling this as 2 pi. A pi bond is there, so 2 pi electrons are involved. So then you see a cyclic transition state is taking place. You know, this is one of the important property of pericyclic reaction. Okay, so the reaction proceeds via a cyclic transition state. Now you can see here that the cyclization takes place and you end up with the product cyclobutane, right? You see it is a 2 pi system. So your m is equal to 2 and n is also equal to 2, and you see m plus n minus 4, 2 plus 2 minus 4, which ends up in 0 pi electrons. So in this particular reaction the end product will have no pi electrons. This is a simple thing which you have to notice here. Okay, so if your system is having m pi electron and n pi electron, you can analyze what type of product you will be getting with how many pi electrons. Okay, so generally it will be represented like this. Okay, normally 2 pi system is there, so 2 plus 2 or pi 2 it's represented, or in the final representation the product it can be represented like this. Okay, this is how you will be representing your cycloaddition reactions. Okay, then you go with the next example. Here I have a different reactant and this B reactant is different. It is as a 1,3 butadiene and here you have the ethylene molecule, right? It is a 4 pi system and it is a 2 pi system. So it has a cyclic transition state. Then you see the reaction proceeds. Okay, it is a concerted mechanism, so you remember that. So it takes place in a single step. Okay, so you see you end up with the product cyclohexene. You have 4 and 2, right? M plus n minus 4 is the formula, right? So 4 plus 2 minus 4. So what is the answer? 4 plus 2 is 6 minus 4, you get 2. So you end up with 2 pi electron system, right? So you have 2 pi electrons over here, that is 1 pi bond. So this is how you will understand the pericyclic reaction of the cycloaddition reactions, right? So this is a general idea about the cycloaddition. Okay, let's go into the FMO approach. Yeah, so this gives a correct idea about whether the reaction takes place thermally or photochemically, right? Okay, let's go to the details. You see here, in this FMO approach, the reaction will be favorable only if the sign of the coefficients of HOMO and LUMO of the reactants are same. So in electrocyclic also we saw the same thing, right? FMO approach considers the HOMO and LUMO of the reactants, right? So that is the thing we are going to take here also. So here the sign of the HOMO and LUMO of the reactant should be same. That's simply like this. Okay, if it is plus over here, then the sign is same, then only you can form a bond, right? So this is what this point means. Okay, you see the second point of the FMO approach here, the possibility of the cycloaddition reaction depends upon the symmetry of the HOMO of one reactant and LUMO of the other reactant. So here the case is different. Electrocyclic reaction is an intramolecular reaction. So you just take the HOMO of the reactant and you just do it, right? But in this cycloaddition, two reactants are involved. So what they are doing is you draw the pi molecular orbitals, and for one reactant you will choose the HOMO, and for the other reactant you will be choosing the LUMO. Okay, let's understand this, how to understand this front end molecular orbital and how to predict the thermally allowed and photochemically allowed conditions. Okay, let me go with the example of 2 plus 2 cycloaddition over here. So this is a very simple example which we discussed in some time before now. And you can see you have two pi molecular orbitals, and this is how you draw the pi molecular orbital and HOMO LUMO. This is for ground state, and this is your excited state, so thermal and photochemical. So in thermal condition, you know, right, this is your HOMO, and in photochemical condition, and this will be your HOMO. Okay, let's first case, we'll discuss the first case, that is under thermal condition. So the same thing happens, right? Thermal condition, you take HOMO of one reactant and LUMO of other reactant. So here Psi1 is the HOMO, and here this is the LUMO for other reactant. So both are ethene, so we don't need to bother about it. Okay, both are the same orbitals. Okay, diagram. Okay, so HOMO of one reactant, right? So this is the HOMO of one reactant, Psi1. So I have drawn here Psi1, and this is the LUMO of other reactant, that is the same ethylene only. So I take the Psi2 LUMO. Okay, I have drawn here. You can see the interaction here, plus and plus are interacting, so here a bond is possible, but here you see the symmetry is not same. What is the first point we discussed here? The sign of the coefficients of HOMO and LUMO of the reactants should be same, but here in the case only here we have the same condition, but here it is not applicable. So what is the symmetry is not matching, so the 2 plus 2 cycloaddition is thermally forbidden, right? So thermally it is not possible. Okay, let's examine the photochemical condition. So for photochemical, HOMO and LUMO you have to take. HOMO of the one reactant. Okay, for this ethylene molecule, the reactant, I take this as the HOMO. Okay, I've drawn it over here. Okay, and I am taking the LUMO. So for the photochemical condition, the excited state will be your HOMO, right? So you will be taking this. So I have drawn it over here, and you know the LUMO, it is the other orbital, and I am drawing it over here, and you see this plus is interacting and minus is interacting, right? So actually it's a plus and minus, so there is no problem when I write it reverse. Okay, it's not going to do anything. So see, both are interacting, both are symmetry matching. So you tell 2 plus 2 cycloaddition is photochemically allowed. Okay, so it is thermally forbidden but photochemically allowed. So you can see here 2 plus 2 cycloaddition means 2 plus 2 is equal to 4, which involves 4 pi electron system, right? So 4 pi electron system stands for 4n system. So your 4n system, that is 4n pi electron system in cycloaddition reaction, is only photochemically allowed, right? You just remember this. So 4n pi system, if you add your 2 plus 2 you get 4, so 4n pi system, it is photochemically allowed. Okay, so you have to remember this. Okay, let's go with the other condition. I go with 4 plus 2 cycloaddition. Okay, see here. So here I have the butadiene and ethylene and everything. I want to know whether for which condition, photochemical or thermal condition is going to be obeyed to form the product. Okay, the same FMO approach I go here, and you can see this is the pi molecular orbitals which you have to draw for your butadiene for reactant A, and for reactant B you see this is your ethene. So for ethene I have drawn. So for reactant A and reactant B I have drawn the pi molecular orbitals, and for ground state I have shown the HOMO LUMOs, and for excited states also I have shown the filled the electrons and shown, and in the ethylene molecule also you can see I have shown the HOMO and LUMO, right? So the electrons are filled. Okay, the butadiene 4 electron system, it's filled here. In excited state the electron is excited, and this becomes the HOMO for excited photochemical condition, and it is all you know it, right? Okay, let's examine. So under thermal condition, what you have to do, you have to take HOMO of one reactant and LUMO of the other reactant. So HOMO for this reactant is this, right, for reactant A, and LUMO for reactant B, it is this. So Psi2 HOMO for this, and for ethylene also Psi2 is HOMO LUMO. So I have taken it Psi2 HOMO and Psi2 LUMO. So now see, I have drawn it. So terminal lobes with signs have been shown, and for LUMO side 2 it is plus and minus, so I just put in reverse, okay, in order to make the bond comfortable. Okay, so see here, it is symmetry matching, and symmetry matching bond can be formed, and it is a thermally allowed condition. So you can see that the 4n plus 2, that is the 4 pi 2 pi cycloaddition, 4 plus 2 cycloaddition is thermally allowed. Sorry. Okay, let's go with the photochemical condition. And you see here, for photochemical condition, this will be our HOMO, right? The psi 3 will be our HOMO. So I just take it. So the terminal lobes have the same sign, plus and minus, plus plus, and you have taken that. And you see the LUMO, the same thing, okay, plus and minus. So you can see this minus and minus is symmetry matching, but here it is symmetry forbidden. So you can understand that it is forbidden. So 4 plus 2 cycloaddition is photochemically forbidden. So 4 plus 2 is equal to 6, right? So it is a 4n plus 2 pi electron system, and it is thermally allowed. Okay, so simply you can frame it like this, right? This is what we have chosen. So 4n pi electron system. So when you add, if you have 2 plus 2 cycloaddition, if you add that 2 plus 2, it is 4. So it belongs to 4n pi electron system. So it is photochemically allowed always. If it is 4 plus 2 cycloaddition, if you add, you have 6 pi electron, it is a 4n plus 2 pi electron system, and it is a thermally allowed case. Okay, so you have to remember this very carefully. Okay. Let's go with the next part, that is the interactions in cycloaddition reaction. Okay, what type of interactions are possible? So because the bond is forming, right? So now you'll see here there are two types of interactions. So one is your suprafacial interaction, and the other is your anterofacial interaction. Okay, so you see here, suprafacial is nothing but both are symmetry allowed, right? You see here, this minus and minus are interacting directly, and this plus and plus, the symmetries are matching, and it is supra, and here it is also supra, and you call this interaction as a suprafacial interaction. In your anterofacial interaction, you see that how the lobes are interacting. This direct way is not possible, but the lobes are interacting in the other way, right? So this you call it as supra when you interact on the same side like this. When it interacts like this, you call this as an anterofacial. Okay, so this is what you call as an anterofacial interaction. Okay, always remember the suprafacial interaction is geometry allowed. The supra-antra or antra-antra, they are geometry disallowed. Antra is not at all possible. So we have the points over here. You can see that all supra interactions are much more feasible as compared to supra-antra reaction. So these are more feasible than that. Okay, then you see the antra interactions cannot occur. They are not allowed. Okay, so you have to remember these points. Okay, I'm just giving the general idea about the FMO and everything, which will be helping for your exams. That's it. Okay, so let's go with the kinetic and thermodynamic phenomena. You just understand the difference between a kinetically controlled and a thermodynamically controlled reaction. Okay, always the kinetically controlled reaction takes place at a low temperature, whereas in thermodynamically controlled it occurs at high temperatures. Here the activation energy is less, and where the activation energy is high. So if you have the activation energy less, so it is more favored, right? So that's why it is kinetically controlled. But here high activation energy, so the barrier will be so big, so it takes much slower time. Okay, then you see here 1,2 type cycloaddition or direct addition are example of kinetically controlled. 1,4 type addition or conjugate additions are type of thermodynamically controlled. These are some marked differences you have to know, which will be helping with some like theoretical questions which will be asked like something, or can be helpful for your for reaction solving and all. Okay. Okay, now so we are coming to the very important part. Okay, so far we discussed about what is the cycloaddition reaction, and then we discussed how to name it, how to name the cycloaddition reaction. Then we went to the FMO approach, right? So after FMO approach, you discussed about 2 plus 2 and 4 plus 2 cycloaddition, and how which is thermally allowed and which is photochemically allowed. So now comes a very important cycloaddition reaction, that is your Diels Alder reaction, a very important reaction which you have to know. Okay, so let's see here. Now we will study a detailed study of Diels Alder reaction in this video. Here you can see that it is a heat induced reaction. Why? You know that it is a 4 plus 2 cycloaddition which involves 6 pi electron system, right? So 6 plus 6 pi electron stands for 4n plus 2, and we saw in the FM approach that it is heat induced reaction, and you also saw that it is a supra interaction. Okay, in the orbital lobes we discussed. Okay, there is one more technique to identify whether it is a thermally allowed or photochemically allowed from the reaction mechanism itself which you approach. When you try to do a ring closure with the number of arrows which you have used, from that itself you can understand the type of reaction, whether it is thermally allowed or photochemically allowed. So I'll tell that. You see here, if you have odd number of arrows, it is a thermally allowed reaction. If it has even number of arrows involved when you do the cyclization, it is photochemically allowed. Okay, how to remember this easily is odd stands for single, right? So odd numbers means like 1, 4, 3, like that it will go. You see, for thermal you put only one triangle, right? So it is single, so it stands for odd. You can remember like that. Even means in photochemical you see you put H nu. H is 1 and nu is 2, so you have two representations here, 1, 2. So 2 stands for even, so you call like this. So let me tell whether it is thermally allowed or photochemical allowed with an example. You see here, when I do this cyclization, you see 1, 2 and 3. So there are 3 arrows involved. So 3 arrows is 3 is an odd number. Odd means only a single, that is a triangle. So you put thermal. So this is a thermally allowed condition. In this case, you see you have 1 and you have 2. Right, only 2 arrow marks are involved. 2 is an even number, so H nu. It is a photochemical reaction. This is one more way, a trick which you can remember easily. Okay, if you have confusions with that 4n and 4n plus 2. Okay, so these are the interactions of Diels Alder reaction. So shortly hereafter, if I use DAR, it stands for Diels Alder reaction. So under thermal condition, supra is more favorable. Under photochemical condition, supra and interactions will take place. So you have to remember these points. Okay, so you know Diels Alder reaction is a 4 plus 2 cycloaddition. It has a concerted reaction because it occurs in single step, and it involves a diene and a dienophile. In your Diels Alder reaction, see here the first reactant will be your diene and the second one will be your dienophile. So you have to remember that there are many properties for that. Okay, so the Diels Alder reaction has certain things to be noticed. Okay, so we have to discuss the characteristics of Diels Alder reaction now. Okay, the first one comes the nature of diene and dienophile. Okay, so see that so the Diels Alder reaction mainly involves diene and dienophile. So their nature is very important. What type of diene we are choosing and what type of dienophile we are choosing, how the reaction is going to take place. So that is of more concern, right? So now I will be discussing here. See, the first point of the characteristic is the nature of diene and dienophile. I just divide it into 3 categories. 1 based on the electrons, and 2 with the configuration, and 3 with the steric hindrance. Okay, steric effect. You see here, electron can be divided as electron rich species and electron deficient species. So your diene can be an electron rich species or electron deficient species. This applies to dienophile also. And then you have less hindered and you have more hindered dienes also. And then based on the configuration, you see we have cis and trans configurations, where cis is 100%. So always for your Diels Alder reaction, your diene should be a cis. It should be in a cissoidal form and not transoidal form. So it is clearly shown here. You should have 100% cis form. Then only your Diels Alder reaction is more possible. Okay, so what we will do generally in the 4 plus 2 cycloaddition, also what we did in the FOMO approach, the same thing. You take HOMO of the diene and LUMO of the dienophile, because this is the first reactant and this is the second one. So for one reactant, if you take HOMO, the other will be your LUMO. In this Diels Alder reaction, you take HOMO of the diene and LUMO of the dienophile. This is what you have to do. And then you see here, we take HOMO of electron rich species and LUMO of the electron deficient species. So when you go with, in case of electrons, see the case is changing. So HOMO of electron rich species and LUMO of electron deficient species. So this is more favorable. Why we do like that is, so it will minimize the HOMO-LUMO gap. So when your HOMO-LUMO gap are small, so the electronic transitions will be more probable and it will have fruitful interaction. So that's why we choose the HOMO and LUMO like this. Okay, so these points are very important. You have to notice that. Okay, so now we are coming on to the dienophile. Okay, so the nature of diene and dienophile also involves the, now we saw about the electron rich and electron deficient species. So we have to bother about the electron donating and electron withdrawing groups generally. Okay, because in questions you will see some groups will be attached and you have to solve them. So you should know some characteristics of those things. Okay, now you see here the electron withdrawing substituent on dienophile, like, so if on the dienophile, that is the reactant 2 of your Diels-Alder reaction. So if it has a electron withdrawing substituent like your carbonyl compounds, so C ketone, aldehyde, COR ester, then CN cyanide, NO2, etc., like this, it will increase the rate of the Diels-Alder reaction. Okay, why? So okay, we will be discussing with some examples, then you will understand the point. And then you see the presence of electron releasing groups, that is electron donating groups on the diene, will also increase the rate of Diels-Alder reaction. Now see, this is your diene. So if your diene has an electron donating group and your dienophile has an electron withdrawing group, this is your diene, this is your dienophile. Diene has electron donating group, dienophile has electron withdrawing group, then the rate of the reaction will increase. Okay, so these 2 points can be understood in this example, so which I have shown in this page. You see here, so you have the diene and you have the dienophile. So there are no substituents, no electron donating or no electron withdrawing group, nothing is there. So just the cycloaddition takes place. Okay, like this. And you see you have the cyclohexene formed over here, and you see it is a normal rate. It occurs at a normal rate, and you see the homo-lumo gap is so far. Okay, so not much favorable, but occurs as a normal speed. That's it. And number 2, the second example, you see what has been done. The diene has no substituent, so you just leave it as it is. But in case of your dienophile, you see you have a COOET. COOET, we saw these things, right? COOR, these groups are electron withdrawing substituents. So the electron withdrawing substituent is over here. So what happens if the electron withdrawing substituent is here? See that it withdraws the electron. So when it withdraws the electron, you can see here that this carbon ultimately becomes electron deficient, right? A del positive appears on the carbon present over here, right? So it keeps on pulling the electron density, so it becomes more electron deficient. So it will it wants the electron because it's electron deficient, so it will ask and accept the electron from here, and the reaction takes place and the ring closure happens and the product is formed. And this occurs at a faster rate than this. Okay, than this occurs at a much faster rate. At a faster rate, that's it. You see the homo-lumo gap is gradually decreasing. Okay, now, so this is in case sorry, this is in case where your dienophile was having the electron withdrawing group. Now the case I am coming here is you have electron donating group and electron withdrawing group on diene and a dienophile. So diene has the electron donating group and dienophile has the electron withdrawing group. So what is the case? You see here in electron donating group, this OMe, it gives the electron, and what happens, this carbon becomes electron rich, right? It becomes an electron rich species, and this particular carbon becomes electron rich. Here what happens, the electron withdrawing group, it pulls and it becomes electron deficient. So this carbon becomes electron deficient. So what will happen ultimately? The Diels-Alder reaction will be more favorable because this needs electron. So it accepts the electron, the cyclization takes place, right? So when the cyclization takes place at a fastest rate than this. So I put 3 ticks over here. Okay, it occurs at a much faster rate and it has more fruitful interaction because see the homo-lumo gap has decreased drastically, right? So the presence of electron donating group and electron withdrawing group will increase the rate of the Diels-Alder reaction. Okay, so this is the order of the reaction: 3, 2 and 1. This will be much faster. Okay. Okay, let's go with this third point which is given here. Okay, if your diene is a cyclic diene, so what is that? So cyclic diene is favored over acyclic diene. So you just remember these points, okay, so that it will be easier for you to solve problems. Okay, later we will be discussing problems in the next video, so there you will be understanding all those things. So you see a cyclic diene is more favored over acyclic diene. Yeah, you see here this is a cyclic diene. Okay, and you have a dienophile, the same thing, and it is thermal condition because it's a Diels-Alder reaction. Okay, if a cyclic diene is involved, the product will be a bridged product. Okay, you remember this point. Okay, so if you have a cyclic diene, then you have to remember that with a dienophile, if you try to do a ring closure, okay, so you see you end up with a bridged product like a norborenyl system, right? Then see the B reaction. Okay, it's a normal reaction. You have electron donating group, methyl group is electron donating group, and you have withdrawing group. So Diels-Alder reaction will be more favorable, and you just do the cyclization and you get the product like this, right? So this is how you have to do it. You see the rate of the reaction, A will be much faster than B because A involves cyclic diene whereas B involves acyclic diene. So remember, cyclic diene is favored over acyclic diene. That's why the reaction in A is much faster rate than your B. So you have to remember this point. Okay, we've discussed this already. You can see about the rate of the reaction. The same thing what I told. Here no substituent, so it will be slower only. Here only one methyl group, so electron donating. Donating means this becomes electron rich, so it will try to give electron. Okay, that's one thing. And here if you see it has two methyl groups. So two methyl group donates, and this carbon becomes more electron rich. So what happens? The Diels-Alder reaction will be more favorable. So more electron rich, so gives much faster reaction. This is how it happens over here. So 3, 2, 1 will be the order. Okay. Okay. Now comes the very important aspect about the stereochemistry of the Diels-Alder reaction. Okay, this is very important part which you have to discuss. Okay. See here, stereochemistry of Diels-Alder reaction. Okay. So suppose if you have a diene like this, and this is your dienophile. Okay, remember, so when you try to do the cyclization and you get the product, the stereochemistry is very important, which we discussed earlier in electrocycling also. We were concerned about the stereochemistry because the products given were ending up with some stereochemical products. So same way here it also happens in the Diels-Alder reaction. So we have a method how to identify it. Very simple. You see, I am putting the groups in the diene as like this, AA and BB. So these are the groups which are inward, and these are the groups which are outward. Okay, rather you can say they are away from the diene like that, and they are inward, they are towards the diene like that. And here you see this X and X, these substituents are on the right side, and Y and Y are on the left side. Now listen carefully. If you have these two types of reactants, diene and dienophile like this in your Diels-Alder reaction, then the away groups, that is the AA here is away, right, outward, and the substituents on the right side of your dienophile should be cis always. See, away group of the diene, okay, that AA, and right side group of the dienophile. So if anything is on the right, anything is away, that is upward and downward. Okay, so they should be cis to each other. You can notice here A and A. See here, we have written in cis, and see the X and X, they are on the right side, they are also cis. See, so these A and X are cis to each other. Okay, this is the criteria you have to follow. So always remember, if you have the diene or dienophile arrangement like this, you can arrange it. You can, if nothing is there, you just put hydrogens and you just balance it, and you try to make the stereochemistry like this. Okay, the away groups and the right side substituents, anything 1 or 2. Okay, the away and the right side substituent, they should be on the cis position. Okay, they should be cis to each other. Okay, so please remember this point, very important. Okay, let's go with this example. You can understand it clearly now. See, I have a diene and dienophile. In diene, you see there is no substituent, so don't need to bother because there are hydrogens involved. That's it. Okay, now we will do the ring closure, and you see 3 odd arrows are involved, and you know it is a thermally allowed condition. Okay, since it's a Diels-Alder reaction, cyclization. Now you see there is no groups here. If it was there, then you will be putting your hydrogens in the cis position itself, right? Like this. You'll put your hydrogen in cis position. Okay, if it was there. Okay, because it's away, like up and down, so you'll put like that. And you see the methyl substituents, see the substituents of the dienophile on the right, so they should be cis to each other. See, this one is also cis, and here also cis, you have cis, and here also cis. So I have written in cis configuration. So this is how you do it. We have more examples. The second example, see, it is a trans dienophile, right? So methyl is here and methyl is here. You can see cyclization had taken place, and you notice here only one substituent is on the right side and the other will be our hydrogen, right? That's it. So only one substituent on the right side. See, on the right will be written in cis. See, so one of the thing is written in cis and the other it is in the opposite side, and you end up with a trans product. Okay, so this is how you do it. And see this example, see, one methyl is up and one methyl is down. This is the case which we discussed in the general form, right? So up and down you have the methyl groups, and you see here one is on the right side and the other is on the left side. You know that right side and this up and down, so the away groups of the diene and the right side group of the dienophile should be cis. See here, okay, those three are cis here. This methyl and this methyl are all in cis, right? But see, the methyl which is on the left side is written different from this, right? See, all have dotted, so they three are cis, but here you have to write it differently because it comes under trans. So you just put the wedge bond, okay, like that. So you remember this, if the diene is opposite, then in the product always be cis. So diene is stereoselective. See here, so if you have your diene opposite like this, okay, so it results in cis only, so it is highly stereoselective. Your diene is highly stereoselective, okay, remember that. And you can note this point also. Okay, so near to the ring, if you see the substituents are inward. If your substituents are inward, you just put it above the plane. If your substituents are found up, down or outward from the ring, you put it below the plane. So above the plane means you put with a dark bond like this. Okay, so below the plane you put like this, okay, with a dotted representation. That's it. So you can see the example over here. Let's correlate it with it, and you see you have the diene here and dienophile. You see this methyl is inward and this methyl is outward. Okay, so what you have to do, inward means put above the plane, outward means put below the plane. See here, this methyl is outward, outward means below the plane, below the plane means like this you have to represent. See, this methyl is represented like this, and see this methyl is inward, this methyl is inward. Inward means you have to put above the plane. See here, this methyl is so here it is here. So here see, you have this methyl on the above the plane, it is drawn like that. See, so this point table, short table will help you to arrange the stereochemistry. And the other part is very simple, which we discussed earlier. It is on the right side, so the substituents are right side, you put on the cis position only. See here, it is on cis position. So this is how you understand the stereochemistry. So see here, the dienophile always be stereo specific, but in case of diene, stereo generally changes, so it is stereo selective. So why we call it as stereo selective? So the stereochemistry is generally changing for the diene, so it is highly stereo selective. This is what you have to understand here. So let's discuss a problem over here. You see here, these ethyl and this methyl, so they are up and down, right? So up down means you just put below the plane. That's the criteria given here, right? So if it is up and down, you put below the plane. So you see the product. So up and down means the product, you see, they are below the plane. So we have drawn below the plane, and see it is on the right side. Right side means it should be in cis, so above the plane. See, we have written above the plane, and this is opposite, so you put in the trans part. That's it. Then the other hydrogens, if you want to show if it is available in the option, just put it opposite to what you have written. So it is dotted, you put in wedge, dotted, you put in wedge, like that you have to do it. Okay, right? So this is how you will be doing it. Okay, now you have to know the types of dienes which are available, that is the configuration. So we discussed about the electrons, electron rich and electron deficient and all. So now we will focus upon the configuration, the cis and trans configuration. So cis, if it is like this, and you can just rotate this and you see you get trans, and again it will rotate and you get the cis. Okay, so this is what the condition happens. But if in trans, if there are groups attached like this, there arises steric hindrance, right? So if there is a bulky group on either side of this trans diene, okay, that you cannot make it again to cis. This cannot be possible. You know that for your Diels Alder reaction, cissoidal form is very important. 100% it should be cissoidal, right? So if you have bulky groups, this trans cannot be converted to cis. But this case is good because it's free, no steric entrance or no bulkiness. But here you have that case and you cannot do this. Okay, so be careful with that. And see, in solution the transoidal form will be 95% and cissoidal form will be only 5%. But we know that for the Diels Alder reaction you need only S cis form rather than S trans form. So you have to choose the reactants very properly, correctly. Okay, why? You see here in trans position, the vacant p orbitals, it has a bond angle of 180 degree and the bonding will not be so easy. It will be very difficult, so it is geometry forbidden. Whereas in case of this cis diene, you see the orbitals are close, bond angle is less, so the bonding is more probable over here and it is geometry allowed. Okay, so these are the points which you have to remember for the configuration part of the cycloaddition. Okay, let's discuss about the regioselectivity of the Diels Alder reaction over here. Okay, so why we have to talk about the regioselectivity is that you can see that the products which are formed, okay, like two or more products can be formed. So which makes this possibility is that the regioselectivity of this reaction. Okay, where this regioselectivity is possible because when your substrate and the reagents both are having unsymmetrical arrangement. So if this is your diene like this, it is symmetrical diene, right? If you divide it, you see up and down it's same, and if you divide here, up and down it's same, so there is no issue. But when I substitute a group over here, it becomes an unsymmetrical diene and dienophile. So your substrate and reagent both must be unsymmetric. In this case, you get variety of products, ortho, para product like that, and it ends up with a regioselectivity. Okay, so in Diels Alder reaction you will notice that ortho and para directing due to involvement of aromatic cyclic transition state. Yeah, so it will involve aromatic cyclic transition states. So ortho and para directing, it can be like that also, ortho para products. So to fulfill this requirement, so regioselectivity of the diene and dienophile must be unsymmetrical. This is very important here. So unsymmetrical, I told you what is that. Okay, so now you have two types of diene I'm considering here. If you have one substituted diene and you have two substituted diene, you imagine that, and you see here for one substituted diene means in the first position carbon you have the substituent, two substituted diene means in the second position you have the diene group, right? So this is what that part of diene. This group can be an electron donating group or an electron withdrawing group. Okay, but they are unsymmetrical, so we go for regioselectivity. If you see the dienophile, the same thing, it can be like this or it can be like this. So in this position you get one sort of diene, so here it is in one position, but here it is in two position. When you react this with this, you end up with like 1,2 product, and if you end up with here, you get other different product like 1,3 product, 1,4 product, like that. So we'll see the examples and you will understand it. Okay, so see here, if your diene is one substituted, if you have a one substituted diene, you end up with a 1,2 product. Okay, it is one substituted means you end up with 1,2 product, and in that case ortho will be your major product. You remember this point. And the second case, if your diene is two substituted, if the substituent is in the second position of your diene, you end up with a 1,4 product, it will be formed, and you end up with the para as the major product. So in that case, para will be your major product. Remember, so one substituted diene means it forms 1,2 product, in that ortho is the major product. Two substituted diene means 1,4 is the product, and you end up with the para as your major product. So this is the small representation which you can understand, okay, with that aromatic ring. Okay, so para product will be almost more probable 100%. Ortho and meta forms in the 50-50 ratio. Okay, so you see here, so you understand here, always electron withdrawing groups are meta directing, electron donating groups are ortho para directing. Meta product in this case will be the minor product. So you remember these points. Okay, these are certain points to be remembered. Now let's go with some examples discussed over here. You see here you have the diene and it is a one substituted diene, right? So you have the substituent in the one position, and see you have the dienophile with a cyanide group attached with an ethene, and it's a Diels Alder reaction. And see the products which are formed, ortho and meta products are formed. So you have an electron donating group, right? So electron donating groups are ortho para directing, where ortho is your major product. Why? Because it is 1,2, right? See here, we discussed it earlier. If you are one substituted diene, 1,2 product will be formed, and that ortho will be the major product. So you omit para. We saw here electron donating groups are ortho para, but which is major? Ortho. So the major product here will be your ortho. You get 1,2 product. Okay. So this is what you get it over here. Then plus the meta will be a minor product, which is told over here. So it is a 1,3 product, so minor product. Okay, so 1,2 will be a major, 1,3 and all will be a minor product. Remember that. Okay, let's go with some mechanism how we call it as 1,3 product and 1,2 product, like that. Okay, how I do this. Okay, see here, I have the diene over here, and the dienophile I have drawn like this, and I do cyclization, and you see 1, 2, 3. So this is a 1,3 product, right? Then see here, this cyanide is here, I put in the other way. I can draw like this and do cyclization, and you see 1, 2. So it is a 1,2 product, right? Okay, it is ortho, and also it is ortho. So ortho is a major product, and this is more favorable. Okay, so when it is asked for any predict the major product or like that, so you should get all these points together and you have to do it. Okay, so please remember that. And then comes the effect of catalyst. Okay. So effect of catalyst explains you something, but generally in pericyclic reactions the catalyst will not do that much of thing. Okay, it's not going to influence that much, but one such catalyst is that the Lewis acid catalyst. Okay, these catalysts influence much. Okay, where you can see that in the AlCl3 is a Lewis acid, you see the p orbital vacant, and in BH3 and ZnCl2 you see you have the d orbitals vacant, right? So the vacant orbitals, they have some role. Okay, these catalysts have some role on the pericyclic reaction, that is on the Diels Alder reaction. Okay, you see the order of Lewis acid catalyst. Okay, it's shown like this. I am explaining with some example. This was taken from Jerry March. Okay, and you see here you have the diene and dienophile. So COOET, I just react it and I get a product. And here you see the diene and dienophile, but here there was no any reagent, but here I add a catalyst, that is AlCl3, and what is going to happen is that the rate of the reaction increases. Okay, see the rate of the reaction is increasing and the yield is also increasing. How? So you can understand it with the mechanism. You see here that it's a COOET group. It is an electron withdrawing group, right? So electron withdrawing group, what it will make? It will make the electron. It will make the dienophile electron deficient. So a del positive appears over here for this carbon, right? This is what happens. So it is one substituted and you have the electron deficient dienophile because of the electron withdrawing group, and see how it is withdrawing the electron. Okay, now I'll do the mechanism. See here. So it is like this, and you have the COOET over here, and I add the AlCl3. I know in Al you have the p orbitals are vacant. What happens? So this oxygen, you can see the mechanism over here, how it accepts the electron density, right? See from the carbon, and it makes it del positive, and here you see the oxygen becomes more electron rich, and that electron rich electrons are given to the vacant p orbital of the Lewis catalyst, Lewis acid. So what happens? Ultimately this carbon becomes more and more electron deficient because the oxygen becomes electron rich, and it immediately donates to AlCl3 p orbital, and this happens, and what happens? This carbon becomes more and more electron deficient. So remember here in this particular case, so when you have a Lewis acid in your Diels Alder reaction, it will make your dienophile is already electron deficient. It should be electron deficient. It will become more electron deficient when you have a Lewis acid catalyst. Okay, so you have to remember, and then you end up with the product. Okay, you end up with the ortho product. 1, 2 will be the major product. Okay, so here you have 1, no, that's why. Okay, so this is how you will be understanding the Lewis acid thing. So that's given here. See, the Lewis acid converts electron deficient. So already the dienophile is electron deficient. It becomes more electron deficient, which therefore has fruitful interaction to be occurred. Okay, so what is the effect of aromaticity on the Diels Alder reaction is that, so the rate of Diels Alder reaction is inversely proportional to aromaticity. Okay, so what happens if you have increased aromaticity, it will decrease the rate of the Diels-Alder reaction. Okay, so you see here you have benzene, naphthalene and anthracene. In benzene and naphthalene the aromaticity is more than in anthracene. So what happens? So Diels-Alder reaction will be favorable for anthracene. Sometimes for trapping of benzene, okay, benzene intermediate, this anthracene can be used, okay, for trapping your benzene. Okay, so this one of the thing, it's an application of Diels-Alder reaction, very important application. And you have other examples, heterocycles, where you see pyrrole and thiophenes are aromatic, more aromatic than your furan. So furan will have it will go Diels-Alder reaction. And you can see over here 1 2 3 4 5 6, you have 6 pi electron system. It's a 4n plus 2, it obeys Huckel's rule, and you know that it is aromatic. Aromatic means Diels-Alder reaction is not possible, but in this case it is not aromatic and it is a cyclic diene. Here Diels-Alder reaction is more favorable. So this is how you will understand. Okay, so in the next video what I'll do is I'll just explain the cis rule, that is the endo-exo rule, how this bridgehead is formed and all like things in the later video. Okay, so you can get from here. Okay, so thanks for watching. So hope you all understood. If you have any doubts, you just post your doubts in the comment section. Okay, later I'll just see and I'll sort out the if any mistakes are there, if you need any further clarifications. Okay, so in the later videos also I'll be trying to make more and more problems and we'll just do it. Okay, thanks for watching.